Welcome, ladies and gentlemen, to this episode. Possibly today we're talking about chemical kinetics. So, chemical kinetics, we deal with a lot of stuffs, a lot of problems. In this case, we're focusing in integrated electro, which has three orders of reaction. Zero order of the reaction with the equation toward there. Then we've got the first order of the reaction. With that equation, I've got the second order of the reaction with also that equation. One thing I'm supposed to put in mind is that all these formulas that have got their own problems, and also all these formulas you can memorize. But the problem of today, or the issue of today, is how to drive the formula of half-life. Or let me say half-life. So I talk about half-life. So in this case, you should know how to drive the formula of half-life of zero order of the reaction, first order of the reaction, second order of the reaction. But in this case, all these formulas are able to memorize. You should memorize, but all what you should not memorize it is their half-life. So how are you going to drive the formula of zero order of the reaction? So I'm going to drive the formula of zero order of reaction with the equation that we have on the table there. So how are we going to do it? Let's go, shall we? We all know that half-life, it is the time taken of maximum, or should I say original reaction, to reach its original value. Should I say it is a time taken of maximum concentration of the reaction of the reactant to reach its original value. So what I'm going to do here, we all know to say half-life in this case can be expressed in form of 1/2. That means that we can try to divide this concentration of A by 2, that means to say we're talking about half-life, or multiply by 1/2, that means to say we're trying to talk about what? Half-life. So in this case, we have initial concentration of A over 2 is equal to negative Kt, which is rate constant times time there, plus initial concentration of A. So what I'm going to do there, nothing to worry more. What I'm going to do, just to need of you to collect light terms there. That means this negative Kt, once cosine equal sign come this side, are going to have Kt changes from negative to positive. Then this side are going to have initial concentration of A minus. Once this initial concentration of A over 2 close equal sign go that side, you're going to have a what? A negative. So negative concentration of A over 2. So in this case, these are light terms that we have collected. What will happen there? That means to say you're supposed to apply some mathematics. So over 1 there, then divide by 2. That means to say this is a common denominator. 1 into 2, it is 2. 2 times initial concentration of A, we're going to have initial concentration of what? Initial concentration of A. Then what operation sign do we have there? We have a negative. 2 into 2, we're going to have 1. 1 times concentration of A, we're going to have concentration of A there. Then we have rate constant times time there is equal to, what is initial concentration of A minus A? By the way, do not try to worry about why are we having, there might be not like terms, nothing more, or should I say there are like terms. Why am I saying so? This more like a 0 there just shows to say it is a initial concentration, but altogether all of them, they are the concentrations. So this is a starting point, it might be a final point there, regardless of that, but all of them, they are what are initial. All of them, the concentration. What is 2 initial concentration minus the concentration? We're going to have only the concentration, which is the initial there, over 2. In this case, note that half-life, it is a time taken. So we're not interested in making K or finding K, but we are interested in finding T, because the T, it is a time taken of maximum concentration of the reaction to reach its original value. So hence, I'm going to divide by K both sides. This one gone. What I'm going to have, we're going to have time there over initial concentration of A divided by 2. You all agree with me if I put a division there, because this divide by sum applies with division there, K. What will happen then? In this case, I'm going to have time there is equal to initial concentration there over 2, then times, so this will change into multiplication. And in this case, as usual there, if I put 1 there, we want to say any number divided by 1, it is itself. So what will happen there, that means to say, changing this division into multiplication as usual, it has affected everything. That means we're going to have time there is equal to 1 times initial concentration. We're going to have initial concentration of A there over 2 times K, you're going to have 2K. Hence, this is a half-life formula of zero order of the reaction. That you should know how to drive this formula. You might meet that in an exam. You should know how to drive it. Do not worry, hence we're going to show how we should solve problem pertaining to zero order of the reaction as integrated electron and half-life formula. Let's move to second order of the reaction. I have first order of the reaction on the table, which is the in as a natural log of concentration of A is equal to negative kT, let constant and time there plus initial concentration as in natural log of initial concentration of A. And in this case, as usual, you can try to multiply it by 1 over 2 because we're trying to drive the formula there, which is equal to 1 over 2 times in of concentration of A, we're going to have in the concentration of A over 2 is equal to negative kT plus the in of concentration, initial concentration there. As usual, the same thing that we did from the first zero order of the reaction, going to like 10, this comes this side, are going to have kT is equal to that which is in of initial concentration of A. Once this in of initial, once this in of concentration of A close equal sign to turn into what? A negative, which is in of concentration of A divided by 2. Allow me now to take you back in the logarithm. You all agree with me under logarithm when we are dealing with subtractions. We all know to say if we have the log of b base A minus the log of A base C, in that case, all we know that all we know that the subtraction turns into division. That means we are going to have log of BC or B over C, because subtraction turns into division, which is log of BC base A, which is that is under logarithm. So log of B base A minus log of C base A, it is equal to log of BC base A. So we apply that concept here. What I'm going to do, we say KT is equal to the in, then open up the brackets, applying that concept. That means we're going to have the concentration of A over 2, or in this case, since we are dealing with, we are starting with this one because that's something that has to remain that side. So I'm going to say the log of, or let's say the in of concentration of, initial concentration of A over the concentration of A divided by 2, then we close. When I'm going to go again, we say KT is equal to the in. What will happen there? We'll do some mathematics to take place there. We're going to have the initial concentration there, divide by, you all agree with me what is taking place here? We're going to say divide by A over what? 2 there. So I'm going ahead to say KT is equal to the in, we open up, the concentration of, or initial concentration there, then that division turns into multiplication. 2 goes up there, we remain with what? The concentration of, or 2 divided by concentration of A there, divided by 1. What will happen once that has taken place? Then I'm going to say KT is equal to the in, open up. What is 2 times A there? It is 2 initial concentration of what? A there. Divide by, what is 1 times that? It is concentration of A there. And what will happen once we have that? As usual, we're going to say KT is equal to, you all believe me what is happening there? We've got A there, regardless of it being initial or what, all of them the concentration. So this means A goes with what? A there, then remain with what? We remain with 2 this side. We remain with in of what? 2 this side. This is in, remain with 2 in, in of 2 that side. Note that We're trying to calculate the concentration. We're trying to calculate or drive in the formula of half-life, and half-life, it involves time. So we're not going to make K as a subject of the formula as a rate constant, but we're going to make T as a subject of the formula there. So which means this K gone, this K gone. What I'm going to remain if I'm going to have T there is equal to in of 2 over what? K. Now, if you try to punch on your calculator, what is in of 2? It is 0.693 over what? K. And what you're talking about half-life being represented with the 1 over 2. So hence, that is the formula of half-life in first order of the reaction that you're supposed to know how to drive it, but you're not supposed to memorize. Memorize the formula, which is the exact formula of integrated electron, but that formula is supposed to know it by heart. That drives us into the third order of the reaction. This is the equation, integrated electron equation of second order of the reaction. Hence, we're supposed to find the half-life of this integrated law of the second order of the reaction. So what I'm going to do in this case, we won't multiply by 1 over 2, but I'm going to multiply by what? 2. Reason why? Because it is in order, or let me say already in fraction. So I'm going to say 2 times 1 over concentration of A is equal to KT, rate constant times time, plus 1 over initial concentration of A. And what will happen there as usual, 2 times 1, 2 there, then concentration of A is equal to KT plus 1 over initial concentration of what? A. You all agree with me, if I try to maintain the weight is that side, you all agree with me that this same applies with 2 over initial concentration of A, when this 1 over, should I say 2 over concentration of A, when this 1 over initial concentration of A equals to cosine to turn into what? Negative. 1 over initial concentration of A is equal to what? KT. That, in terms of, or let me say, the way I've corrected the items is one and the same. We should correct it in other way around. So what will happen there? As usual, find the common denominator. Not to say the common denominator will be the what? Initial concentration of A. Reason why? Because each and every reaction is starting from its initial point. So what will happen there? What is 1 into initial concentration of A? Possibly they are going to remain with only 2. 1. 1 times 2 it is 2. Minus that into that is 1. 1 times 1 it is 1 there. Then what will happen this side? We're going to have KT then is equal to 2 minus 1 it is 1 over initial concentration of what? A there is equal to what? KT. Not that we're not looking for K, but we're looking for what? T. Hence, make K as a subject or T as a subject of the formula. That means we're going to have T is equal to 1 over initial concentration of what? A. You agree with me that this over turns into what? Division, which is like that. Then what I'm going to do there, it's one and the same. Then you say time is equal to 1 over initial concentration of A, or not to say there anything divided by 1 it's itself. So hence this division to change into what? Multiplication. 1 goes up, K down here. You're now going to have T is equal to 1 times 1 is 1, K times initial concentration of A, it is K initial concentration of what? A. Then we are talking about half-life. Hence, this is the formula of second order of the reaction that you're supposed to know how to drive it, but not memorizing it. You can memorize integrated electron, the second order of the reaction, but not memorizing. But not half-life. Hence, this marks the end of how to drive the formula of half-life. Let's try to solve some equation, should I say, some problem in this case. Thank you.